welcome everyone. So, good afternoon. Welcome to the robotics seminar. So today we have, Jeffrey Ichnowski with us. So Jeffrey did his bachelor's from UC Berkeley, specializing in computer science and Asian studies. Then he went up to, he did his PhD at North Carolina, and he decided to come back to the Bay Area and do his postdoc in Rise Lab and in Auto Lab, working with Ken Goldberg. So Jeffrey has done a lot of interesting work, including a recent science paper, talking about motion planning, but also a lot more work in, learning and optimization for manipulation. So super excited to have you here, Jeffrey. Please take it away.
All right, thanks. Yeah, I'm super excited to be here. Thanks everyone I've met for your hospitality. So I'm gonna get to my talk that I'm titling Dynamic Robot Manipulation, Learned Optimization, Deformable Materials, and the Cloud. But really, this is more my talk about how I like to make robots go fast and compute fast. So a lot of my research started off, just to start the groundwork, looking at separate interests. Like, let's do a grass plan, let's do a motion plan, let's do time parameterization, or treating the world as rigid, or looking at how can we speed up this limited computing capabilities that we have in robots. And now these separations of concerns are good. Like, engineering standpoint, they're great to have. We get great models, great theoretic results, good practical results. But now my interests are more in what can happen when we start combining these things together. If we do grasp and motion planning at the same time, can we have a faster motion because we can have that grasp perturbed towards having a faster motion? Or if we do time parameterization at the same time as we do the motion planning and the grasp planning, can we do something where we get very fast motions that have all these things incorporated in them? And if we can start to lift these quasi-static constraints, what sort of new manipulations can we do? I've also been looking at deformable manipulation and specific dynamic deformable manipulation. So this non-rigid, from this rigid world to a more dynamic world. And as a result, we can speed up, operations like folding, packing. We can start to manipulate objects out of reach, like this power cord is able to be manipulated over a distant obstacle. And I'm going to do something which I don't know if it's the first year, but I'm going to do a citation from a prior talk here. Why do dynamic manipulation? And I can't do justice to Matt Mason's work, but this is his slide up there. I'm sure everyone can read it. And so the last thing I'm going to talk about is using the cloud. And the reason why I'm proposing the cloud is because we want to be able to compute things fast in a lot of cases. And if we get the power of the cloud, we can speed up things by 100-fold and make things that used to take more than a minute to compute, to make them compute in a sub-second. And we can start to have much more capabilities out of our robots that we might not have been able to have unless we waited 10, 20 years for the computing capabilities to catch up. So here's the agenda. I'm going to talk about this combination of grasp motion and time parameterization, learned optimization, dynamic deformable manipulation, and cloud robotics. So just to get started on the first agenda item. So e-commerce. E-commerce is exploding today. It cannot keep up with demand. So this has been a huge motivation for this line of work. How do we keep up with demand that's been imposed by the pandemic or by social distancing required within warehouses? And a lot of warehouse operations boil down to pick and place, whether it's from bin to bin or shelf to shelf or bin to shelf or some other combination. And the pipeline, if you look at it, looks something like this, where you have, at the front end, you do some imaging, segmentation, you do grasp analysis, and then you do your motions to reach to pick and pick to place. But due to all these advances we've had in deep learning, that front end of the process is now just insanely fast. And our motions, the physical motions of the robots, are dominating the cycle times. So if we start off with a grasp analysis, say something produced by DexNet, grasp analysis gives these contact points that says we can lift up this object safely robustly, and the object will not fall out of the gripper. And in a normal operation, pick-and-place operation, a gripper might go and take a top-down grasp and lift up the object and go around. But we realized what our key insight here was, this actually implies a degree of freedom that we can incorporate into our motion. Any of these poses around those contact points is something that we can use to speed up a motion if we can get our optimization to use it. So I'm going to give a bit of an overview of how we do this. This may be some material that everyone's familiar with, but it lays the groundwork for a lot of the other parts of the subsequent presentation. So we came up with something called Grasp Optimized Motion Planning, GOMP, where our objective is to minimize trajectory duration subject to the constraints that I mentioned, that we have this grasp analysis constraints, we want to avoid obstacles, and we have the joint limits that we need to obey. So of course, those first two sets of constraints are non-convex, and the way we approached this was to discretize a trajectory with a fixed time step and place it into an optimization. And we're having this quadratic optimization where our objective is to, in this case, minimize the sum of square accelerations. Other formulations are, of course, possible. So first I'm going to describe how we minimize this, and then I'm going to describe how we minimize the time on it. So just putting together our optimization formulation, we have our joint limits, the configuration limits, the velocity limits, acceleration limits. We have our boundary conditions that we want it to start and stop with 0 velocity. And we add in an MPC-style constraint between each of the waypoints that we've discretized to. And then for the non-convex constraints, we use essentially trajopt, the formulation that they have. And the way this works is that you take an obstacle, for example, this bin wall that we're trying to clear, and you want to keep the robot out of that. But since we're optimizing in the joint space, we need to go through the Jacobian and do linearization of the constraint. Of course, this linearization is only good for part of the motion. If we optimize, if we continue to optimize, it will be invalid. So yeah, this is what it looks like. And I will get to that in a second. And so we also do a similar thing for that grasp constraint, but now we have to do it about that rotational degree of freedom. So now that we have all these constraints put together, we have this large optimization, and then we solve it with a trust region-based sequential quadratic program. And high level, the way this works is we linearize our constraints, form this A matrix of constraints. We solve our QP, and if the solution improves, we accept that solution and just iterate until we get convergence. And I'm skipping over the trust region and penalties and then are involved in this, but those are details we can go into some other time. So the time optimization that we do is after we have this solution to our motion planning problem, we have a trajectory that looks something like this. The top is our joints configuration over time, the middle is our joint velocity over time, and the bottom is our joint acceleration over time. And what we simply do is we repeat the optimization, shrink the horizon until we get to a problem that the SQP solver detects as infeasible. We're able to get a lot of efficiency out of this because we can reuse solutions from the previous iterate to warm start the next iterate. And one of the things I want to point out here is that this trajectory has properties of time optimal trajectories where at any point in time, one or more of the joints is at a derivative limit. It's at a velocity limit or an acceleration limit. So we put this all together. We get a very fast pick and place. We beat our baseline by a significant amount. And one thing that's actually kind of surprising is that our bottleneck actually became that gripper close speed. The gripper takes more time to close and open than the motion in this optimization, after this optimization. So we took a deeper look into this, and we found that without jerk limits, so we weren't doing any jerk limits, and just some implementation details, this robot is an industrial robot. We do not have access to directly control its motor torques. We have to tell it the trajectory that it's following, and its internal black box controller is doing its best to follow it. But the problem is, without the jerk limits incorporated into our optimization, if we play back the planned trajectory and overlay it with the trajectory we get from the encoders, we see that there's overshoot at the end. And that's due mostly to not having that jerk limit. The other thing, of course, we're worried about is stressing the joints and wearing out the motors over time. Now, the thing is, we added jerk to this optimization, and a surprising thing happened. The compute time blew up to 28 seconds median time, which, of course, is really not useful for sub-second motions that we're trying to get. So we don't want to spend 28 seconds to get a sub-second motion. So this leads into the learned optimization aspect of the talk. So we looked at speeding up this computation from two sides. We sped up the outer loop and the inner loop. Oh, yeah?
But if I just, so our torque, I know the URs don't give you access to torque, but are torque limits a thing? I mean, if you were carrying a heavy object, would you still be able to live near those acceleration constraints published by the UR, or is this a...
You have to adjust your acceleration constraints proportionally, yeah.
You adjust them in proportion to the weight?
Yeah.
That's a good enough heuristic? Or?
Yeah, it seems to me, yeah. I mean, we could probably push it a little bit more if we directly incorporated a lot of those constraints. So far, we're going kind of fast enough for our purposes. So we're speeding up. I'm going to talk about speeding up the outer loop and the inner loop, and start off by this outer loop. And so this outer loop was our Science Robotics paper, where the idea is, let's see if we can just take this pipeline from before, where we have this input trajectory, we run it through our SQP, minimize time, run it on the robot, and see if we could do deep learning to make to learn the function. Could we have it just play back trajectories that execute as fast as our SQP was able to do? And so we trained this, generated a whole bunch of random inputs from our distribution that we're likely to expect in runtime, from the pick bin to the place bin, run it through our optimization, generate a data set, and then train a neural network, and then try to run these trajectories. Now, the problem is that these trajectories that the neural network was able to produce were sometimes not runnable. And the reason might be obvious to many, but the idea here was that these neural networks are not able to accurately produce all these tight constraints that we were trying to get out of the motion. So any misprediction on one of these things, on one of these derivatives that is right at the joint limit, will cause the robot not to be able to follow the trajectory. So our key idea here was, well, we were actually able to, I'm glossing over a lot of details, but we were actually able to train the neural network to be really good, really close. And with that, we were able to feed that in as a starting point to our optimization. We were able to warm start our optimization and get the best of both worlds. So we get this really fast forward pass of the neural network to get the trajectory in just a few iterations of our SQP, and we get the constraint satisfaction that we need to run on the robot. And with that pipeline, we were able to speed up our motion planning from 28 seconds median time to 80 milliseconds median time, a 300x speed up. Yes?
Yeah, so in the previous slide, you mentioned using the neural net to produce the warm start trajectory. Mm-hmm. Is that trained in a special way, or was it trained in the same way as before, where it's just trying to predict the end trajectory and not producing a good, an actual one that satisfies all the constraints, yet still providing a good enough warm start?
Good question. Yeah, we were training it the exact same way. And I do want to emphasize that I glossed over a lot of details. We had to make the function essentially learnable, and that takes a lot of engineering effort that I can go into detail at a later time. So that was the outer loop. Now I'm going to talk about speeding up the inner loop. So the inner loop of this optimization is a QP. And QP, I'm sure many know, but just to get the notation out, is solving a quadratic cost or minimizing quadratic cost in that P matrix is subject to the linear constraints in that A matrix and the lower and upper bounds. So we're using this QP solver, OSQP, And it has a lot of these really favorable properties that we were taking advantage of, including that it's warm startable. But when we were generating all this training data, it was sort of agonizingly long to generate a lot of data. We spun up hundreds of cores to try to generate data faster. So we tried to see if we could speed up the optimization more. And I found out a way to do it, and I reached out to Bartolomeo Stellato and Goran Banjak, the first authors of OSQP. We formed a collaboration, so a big shout out to them for their help with this. And here's how we did it. So high level, the way OSQP works is it sets up a matrix with the quadratic objective and the constraints, and then it performs a linear solve on that matrix and performs ADML updates projecting onto the bounds until it converges to a solution. Now, one of the key parameters in this, or tunable parameters in this optimization is that row vector, which has a significant effect on the convergence rate. And it has also these interesting properties as well that theory shows that it will converge regardless of value. It just will take longer or shorter depending on the value. And it's also OK to change between iterations with some caveats. And the optimal value for this is not known, or maybe intractable might be the way to put it. So OSQP has this heuristic that they were using to adapt row between iterations, and this is what it looks like. High level, it has this row bar scalar that it adapts based upon the residuals. And it then makes a vector out of it depending on the coefficients, depending on whether or not it's an inequality or equality constraint. And so our idea was, could we learn a faster row adaptation policy? And our proposal was to treat this like an RL problem, or frame it as an RL problem. And so our environment would be the QP. The state would be the internal solver state, so it would be completely observable. The action would be that row update. And the transition function would be the ADMM iteration. And the reward would be to encourage it faster in convergence, to just give it a -1 reward for each step it takes until convergence. So OSQP looks like this. It has this heuristic adaptation policy that it was using. And RLQP, what we proposed, looks like this, that we have now an agent that is adapting our row as we solve the QP. And so our first iteration of this was to solve for that row bar scalar and use the heuristic to create the vector. And so we used TD3, DDPT. It actually didn't seem to matter much which one, and we learned this policy and got reasonable results, which I'll show in a little bit. But we wanted to see if we could do better and see if we could come up with a way to adapt each individual component of that row vector as well. So the problem is that that's kind of a non-trivial framing of the problem that we want to solve here. So we want to remove that heuristic that I mentioned, that we want to just learn row to be some policy. But row, the vector, is sized according to the number of constraints you have in the QP. And the size of QPs can vary from one problem to the next. And any permutation of those constraints is still the same QP. So we have to be permutation invariant, and we have to deal with this varying size QPs. So our idea was to train a policy that we're calling the vector policy. It's really a multi-agent policy with a single policy that we train for every single value of row. And we used an idea from this paper called One Policy to Control Them All, where we, if you look at the difference, I know there's a lot on the slide, but if you look at the difference between the scalar policy and the vector policy, really what it amounted to is stacking in all the state into our training buffer and appropriately, or replay buffer, appropriately growing that replay buffer. And so we ran this on existing standard benchmark problems and compared performance. And so here's the results. So the vector policy, the purple one, was able to outperform OSQP's baseline heuristic policy in all cases, and tied in one case where it was essentially one iteration. And in some cases, we were able to start outperforming Gurobi, a very popular commercial solver. We also wanted to look at the learned policy to see if we can analyze something from it. Yes?
So you mentioned there are some caveats on how rho can vary. Usually that's something about it has to be decreasing over the iterations. How do you enforce that with the neural network?
So we didn't have to force it and learn that. But the actual thing that I was talking about, the caveat, the big caveat is you can't change it too often. If you change rho too often, it sort of bounces around and doesn't converge. But yeah, the policy, we can sort of look at this slide, which maybe answers that a little bit. But we looked at the policy to see if we could see properties of it that we were hoping to see. And we found that it did exhibit these theoretical properties that we wanted to see, that it was low where it's supposed to be low, high where it's supposed to be high. And you can see it's highly nonlinear. Yeah, I think, did that answer your question, or was there something else?
It was more of a question of like, can you guarantee that? Because if you don't change rho too often, you're guaranteed to converge.
Right.
But is there some condition on how rho has to change over time? As in, it has to be monotonically decreasing so that you don't end up thrashing around near the optimum or something?
No, it doesn't actually have to be monotonically decreasing, at least in my experience. Maybe I missed something, but I think when we looked at it, it wasn't monotonically decreasing in many of our examples, and it was still able to converge. Yeah. All right, so I'm going to get on to.
Can I ask
Oh, yeah.
the solver state is problem size specific too, right?
Yeah.
Did you have to do clever encoding there? And like, you really have a sense that this is working for very small QPs and very large QPs, and maybe you could speak to that.
Yeah, so I have results on that I didn't put in the slides, unfortunately, but we did do dimension scaling analysis, and we saw that it scaled really well within, as we increased problem size from some very small, like 10 to 2,000 dimensions, we saw a very nice growth in curve that we were expecting. And yeah, I mean, part of it goes back to these benchmarks that come from the OSQP set, that they are tunable to different sizes, and that we could actually fiddle with the problem size and generate that data. Moving on to dynamic deformable, my slide was a bit of a lie. There's actually 3 parts to this, not 1 part. So, getting back to our motion planning, we found that we were moving the robot too fast. Fast enough that when we have an open top container, everything starts to fly out of it and nicely flies out of it at the peak there. And at this point, I should probably give a big shout out to Yahav Avigal, who spent his time cleaning up those beats. So what we decided to do was introduce inertial constraints. Basically say, let's compute that the acceleration experienced at that end effector and use that to form a constraint in our increasingly growing optimization to constrain it so that we're never exceeding a tilt angle in which contents will spill out. And here you can see really what I found cool emergent property of this is that we just specified this constraint, and the robot, the optimization figured out that it could kind of go back and build up momentum to swing over the top. And you can see that right at the beginning there. And the next thing we did was say, well, let's adjust that constraint. If we have a 15-degree angle that we want to keep the contents in the container, we have to necessarily move slower, but if we have more tolerance before spill, so if we can tilt the container 45 degrees before contents will spill, perhaps we can move faster, and we can. And this part, I think, is also a cool emergent property, is that we actually see the beads go upside down, that if we were to try to plan this statically, quasi-statically, and then time parameterize it, we would not get that, we would not come close to that capability. So we looked at some results on this and wanted to see what that trade-off would be like. If, what's the fill level have to do with the trajectory time that we generate? So as you might expect, as you get more and more tilt tolerance, tighter and tighter constraint on that tilt, it takes longer time. And as you're clearing a higher obstacle, which is the x-axis here, you have to go slower. So the next challenge, and this fun story was a challenge from Ken Goldberg about 8 hours before the deadline for the paper was, could we do it with wine? And we did, and here's what it looks like in slow motion, which of course was that first slide. Yeah, real fun project. And I want to point out at this point, there are no wine drops on that cloth. All right, so dynamic deformable manipulation part 2. So we also wanted to see how fast could we move things in suction. You know, a big problem with suction is if you lift up an object too quickly, it's going to peel out of suction. Yeah.
How are you guys determining the tilt constraints? Are you just kind of hand coding different ones and seeing which ones are suffice to prevent, or are you actually learning sort of what the boundaries are?
So for the tilt constraint, we literally say if this object spills beads at 16 degrees, then our tilt constraint is 15.
Okay, so you're just figuring that out, sort of.
Yeah. So
Okay.
the actual in like engineering production, we would have to have some sort of classification network or vision system to analyze and figure it out.
Thank you.
Good question. Yeah. All right. So suction transport. If we move too quickly, things will come out of suction, and so our problem here was, could we now move things in suction without having this grasp failure? And the idea, initial idea is, let's formulate this as a bunch of analytic constraints. Let's say we have this, the suction friction cone that we want to keep. We want to keep the suction force within a threshold. We want to keep the moment balance, and we could, continue to come up with models and analysis for how to keep this in the suction, how to formulate these constraints into a suction, to keep the suction grasp through a transport. But one of the things that we looked at was when you look at the slow motion video capture of these, what happens is there's actually a deformation of the suction cups before the suction breaks. And in that time, if the robot sort of pushes back, it will retain suction. So how do we do this with, how do we come up with an analytic model for this? Well, there's actually been some really good work on this, but it involves coming up with spring models or finite element models and somehow wanting to integrate that into your optimization started to become a daunting task. And we also have this problem that, if we start considering deformation, well, the contact area changes. So it sort of feeds back into all of our other constraints about keeping the friction contact stable and so forth. So we said, why don't we say this is really difficult to model and see if we can learn it. And so we wanted to formulate this constraint, this G function that is sort of a probability, and I say that with quotes because we're really just using it to threshold, to keep that deformation as part of the constraint. So we set up this self-supervised learning pipeline where we first collect a whole bunch of self-supervised data. We do some data augmentation. We train this function. We get a neural network. And to make this training really efficient, we built this 3D printed suction gripper. And the sort of key point here that made this really easy and possible is we have that pressure sensor outlet that allows us to detect when suction breaks really quickly and really reliably. So our self-supervised learning system essentially just lifted the object vertically with a whole bunch of different motion profiles and did that then at different angles as well so that we could control for gravity. And we striped through a whole bunch of different angles for different masses. But we were able to use some domain knowledge to speed up our training process. We essentially could do a boundary search saying that, as we start exceeding the break threshold, we can, start looking below that and so forth. And so we really reduced the amount of training that we had to do. And of course, we used domain knowledge to extend this to say that any time that we have a successful transport without suction break, if we go slower, we still can we can label that as a success. And anytime we go faster than a suction break, we can label that as a failure. So we trained this neural network, and one of the things that we had to take into account as well is that the deformation, as we showed in those 3 stills, takes time. So we trained the function to have a history of inputs, a history of accelerations over time, and we just determined that history by counting the number of frames that we saw in the video between when suction deformation started to happen and when the suction break occurred. And we just really simply trained this with labels 1 and 0 for success and failure. Sorry, reverse that. And then the problem comes up is how do we integrate this into our constraint? We have this function that we need to linearize into our optimization from before. And the nice thing here is that we could just use the autograd straight out of the network. And so this forms our online process where we take our inputs, we run it through our SQP from before, and we linearize that constraint and use the Jacobian from the network to help that with that. And then we get reliable transport of objects in suction without the suction failure happening. And so when we look at some of our baselines, we compared this to 2 analytic models. I'm going to call them optimistic and pessimistic. And really, it just amounts to how much modeling we put into it. And you can see that our pessimistic model was able to get 100% success rate with this. And similarly, our trained models on the right in green were also able to get high success rate. And we have this threshold, this D-safe threshold that we're varying to see how that threshold affects reliability of the transport. And you can see if we have the threshold too high, that objects drop out of grass. And then we also ablated whether or not history has an important effect. So we just trained with our history being 1, so no history, and we got 0 success rate. So that having that history of state over time was really important for part of this. So the result was that we look at the timing as well, and we see that we get a 16 to 58% speed up depending on the mass compared to that analytic model. And we also see that we were able to generalize to this unseen mass of this 1.6 kilograms. And here's another sort of view on that generalization that we computed in simulation a whole bunch of trajectories for different thresholds and payloads. Those are on the bottom axis, and then wanted to see how long that trajectory would be, which is the z-axis. And we get the effect that we were expecting to see, that we see a relatively smooth output of this, and we see longer trajectories for lower safety thresholds, higher safety thresholds and higher mass. All right, so now we're going to get on to dynamic deformable part 3. And this one is a fun project inspired by Raiders of the Lost Ark, and probably my favorite titles of papers that I've been on, Robots of the Lost Ark with a C. And the idea here is we wanted to see if we could manipulate cables to go over distant objects. So I would call this the stuck vacuum cleaner power cord problem. You're vacuuming along and you want to get your vacuum over there and the cable's stuck over there. So what would a robot do? Well, it would normally just traverse back. We wanted to speed that up. And so the way we set this up was we have this fixed endpoint on the wall where it's plugged in, and the gripper is holding the other end. And we approached this sort of borrowing ideas from TossingBot, where we said we're going to have this fixed start and end pose for the robot, and we're just going to learn this apex parameter, this apex of the motion, and we're going to fill in the trajectory with a trajectory function, which just happened to be GOMP from before. However, there's a problem that we observe that if you have the cord laid out, however it just happens to be, it's really sensitive to the initial condition. So this is 20 different trials, exact same motion of flipping that cord, different initial conditions, and we get results that are all over the place, including one failure you can see. So our solution was to come up with a reset motion, which simply pulled the cord up and down to get it laid out flat and straight on the ground. And once we did that, we got really repeatable motion. So the exact, really repeatable results. So the exact same motion would get this overlay on the bottom that you can see there, on the bottom right. So our pipeline on the robot is on the top. It resets the cable. It then goes through a ResNet to predict that apex point, does the trajectory optimization, and then runs the trajectory. And of course, we had to background them in our algorithm name for the self-supervised learning. So we have Indy. And the nice thing, so you don't have to read the whole slide, but the nice thing that we were able to exploit here is that we could train left to right and right to left. There was no reset problem that we had to deal with, no manual human intervention to put in. And so we tried it out in the vaulting experiment, where we can vault over distant and nearby obstacles. We can knock targets off pedestals, which don't ask me the utility of this. If you guys have ideas for the utility, it's more a demonstration of the capabilities, but I don't think we want robots doing this. And then we also did weaving, where we weave between obstacles from near or far and at different separation. So the results on this are pretty good. I think we could do better. Would love to discuss how we could do better. And one thing I don't want to skip on that is this huge shout out to Harry Zhang, who was an undergrad, who's now at CMU, who did a bulk of the work on that project. So the other work that we've recently done is free end cables and trying to hit a target trying to hit a target on a sliding surface. So we now have to deal with the frictional aspect of this as well. And we set up a self-supervised, we set up a system that looks like this. We do a whole bunch of physical data collection, and from that, we tune a simulator to match as close as possible using differential evolution. And, we then collect a whole bunch of data in simulation and train a policy. And we also pipe in the physical data trials as well to learn this policy to hit the target. And probably the most interesting result from this, I find, is that when we train just on physical or just on simulation, we don't do as well as when we train on both. And sort of the intuition, I think, is that we have really high fidelity data from the physical trials, but we don't have a lot of them. And we have a lot of data from the simulation, but it's not as high fidelity. And so with that, I'm gonna move on to cloud robotics. And I'm just gonna, I haven't figured out a smooth transition here. I'm just gonna go from dynamic deformable manipulation to cloud robotics, yes? Yeah.
So you're using some modeler tuning to train the simulator, but then in step 4, you're just using policy learning. You're not doing anything you're not doing model-based learning in step 4.
Right.
Okay.
All right, so, yeah.
So you're mentioning that you can get pretty repeatable behavior, I guess, when you're initializing. How much did it matter? It looked like the rope was initialized very close to the block that you were flipping over. So if you moved it far away, did that matter? Or oh, I see.
Did the picture answer your question? Did the picture answer your question, or I'm sorry, I was going back to the slide. This is what you're talking about, right?
Yeah.
I'm sorry, the reset motion as well?
Yeah, the reset configuration.
Mm-hmm.
So how much did the repeatability depend on what that choice of the reset configuration was? Or didn't?
So if I understand your question correctly, maybe I'm not, there's really only one reset configuration we have here, which is pull tight, and it's just the line between the wall and the robot where we lift it up and lay it flat.
Okay, so it was specific to that one.
Yeah.
Got it.
Yeah. We try on multiple cables as well and show results for that as well. Okay. I don't know if I fully answered your question, but looking at time, so I'm going to move on, but maybe we can get back to that later. All right. Oh yeah, and I wanted to give a big shout out to Vincent Lim, an undergrad at Berkeley, who did a huge amount of work on getting that simulation tuning to work. And then, so now cloud robotics, no good transition. So one of the things that I've been thinking about with cloud robotics is, the computational aspect. So I talked a lot about like speeding up the motion before. Now I want to talk about like how do we speed up the computation for these motions. So a big motivation for this is that all these different robots have limited computing capability. They have it due to battery requirements, mobility requirements, weight or cost, or even just age. Like a robot might last 10 years and still have a 10-year-old processor in it. So on the contrast, in the cloud, if you can suffer the latency and bandwidth to get to the cloud, you get access to enormous amounts of computing. And of course, there's these concerns about outages, security and privacy. But right now, I'm going to do what all good scientists do and just assume those out. So let's say we have a robot that wants to get around a room. I'm sure everyone is familiar with sampling-based motion planning. Well, one of the ways we can speed up motion planning is just exploit multi-core parallelism. Just sample really efficiently on a lot of cores simultaneously. So here's an example from early work I did with speeding up motion planning using lock-free parallelism. And the idea with lock-free is that these threads are computing samples, checking them and adding them to the tree. But when they're updating these shared data structures, they're not paying any overhead for locking the shared data structures. They're just doing an update in a safe way that they all see it. And we extended this to run on 72 cores in the cloud. So here's a cloud-based 72-core motion plan doing whole body motion planning for 18 DOF robot motion planning problem. And to show another perspective on this, here's what the H-top looked like when we were running that. We were pegging all 72 cores. And the real fun part is that if you look at the stats, we got 1 hour and 45 minutes of computing and under 90 seconds of wall clock time. So another way that we looked at speeding up this cloud-based planning is could we split robot and cloud-based computation so that the robot can react to dynamic obstacles. And the way we approached this was to have the cloud computing this huge roadmap, but just sending the relevant portions to the robot so that it would have options to navigate around a novel obstacle. And when we applied this to a manipulation problem, here I am torturing the fetch robot, where it's got this plan coming in from the cloud, and I'm presenting a novel obstacle that it is computing locally based upon this larger map that the cloud is computing. So one of the things that comes up, though, is that having an always-on high-end computer for this type of problem is not really an efficient use of resources. That you have robots, let's say we wanted to have a robot declutter this building, it's going to have navigation problems and manipulation problems. And the navigation problems are low-dimensional, the manipulation problems are high-dimensional, which require different amounts of compute. And there's also times where the robot is just moving and not needing any compute. So we could plot the CPU usage over time, and it would look something like this. And then maybe occasionally you get a really complex decluttering problem like this. So we looked at, could we speed up motion planning using serverless computing? And serverless computing is high level, you give a single function, the code for a single function to the cloud provider, and then you run it whenever you want. And the nice thing here is you build in 100 millisecond increments. But serverless computing has a lot of limitations. I'm going to skip through all of them except for kind of the most important one is that you don't get any additional computing over what you might have in the robot. You've got 2 threads, maybe at max on that serverless instance. So the idea is if one multi-core Lambda is too slow, maybe we can use a whole bunch of them in parallel. So you're probably also familiar with these 2 guys as well who came up with RT. So RT star. And so what we did for this acceleration, for speeding up RT star using multiple lambdas in the cloud, was we made use of this heuristic where you could speed up motion planning by rejection sampling anything outside of what's possible to improve the best path found. So it's really a combination of two parallelized motion planners, one that parallelizes within the lambda, one that parallelizes across lambdas. And when you run them together, all they have to do is share that best path found so far, and it improves the ability to sample faster and produce a better solution. So we could run it on tens of lambdas simultaneously, or hundreds, or even 1,000 lambdas simultaneously. And just to show what the results look like on the standard OMPL benchmarks, we can see that our convergence rate dramatically improves using multiple lambdas simultaneously. So I'll skip through the rest of these examples, but you see similar results, that you just get massively faster convergence on all these problems using 100 lambdas compared to the fewer lambdas. And we apply this to a motion planning, a manipulation problem, and compare 1, 10, 100 lambdas executing the same problem for the same amount of wall clock time. And you can see that the 100 lambdas using that asymptotically optimal motion planning can find a solution that reaches the target much faster than the 10 lambdas. And in the same amount of time, wall clock time, that one Fogross lambda or the robot itself essentially equivalently could not find a solution. So hopefully I've convinced you of the power of the cloud. Maybe you're already convinced. The question is, can we get access to it easily? So this is a recent development that we're publishing shortly. So you guys get a sort of a preview of it. And the idea, we're calling it Fogross. That's Ken's idea for a pun. And here's our Fogross duck, robot duck. The idea is that ROS is like the de facto standard for robot development. And we want to make use of ROS to deploy nodes to the cloud easily. So let's take an example application. You have something like this where the robot is doing both grasp and motion planning, and the grasp planning benefits from a GPU, and the motion planning, as I just showed, benefits from lots of cores. But the robot only has 2 cores and 1 GPU. With Fogross, what you say is, let's annotate the launch script. That's it, no change in code, to say, let's move that grasp planner node to a GPU instance in the cloud. And Fogross takes care of the rest. It sets up a machine in the cloud, sets up ROS on it, moves all your code to the cloud, all the dependencies, sets up secure communication, and also optionally compresses the video stream to the cloud so that you can start to do things like SLAM in the cloud. And so with our examples here, we have SLAM done in the cloud, just deployed through Fogross, and we get a 2x speed up, half the latency. When we do GPU planning with the cloud, including the latency of the network round trip, we get a 12x speed up. And when we do motion planning, just moving to a 96 core cloud computer, we get a 28x speed up. And I think we can actually get more. So that's actually it for my presentation. And I want to give a huge shout out to all my collaborators, and some of which were on these papers, some of which are on papers that we've published separately. They've made this whole problem of robot research really interesting. I didn't find all their pictures, but here's a lot of their names. And with that, I will say thank you and ask if you have questions.
Thank you, Jeff. So we do have time for a few questions. Anyone? Yes.
So I'm super interested in the cloud stuff, but I didn't quite get it. I'm sorry, it just went a little fast for me. So what exactly is the contract you have with a Lambda provider, and what is Lambda? Like, what did you send as your Lambda? You said it was the path only, but that...
Yes, I realized I went very fast through that, so thank you for your question. It allows me to answer more clearly. So we know that with RT star that we can speed up sampling by rejection sampling anything that doesn't speed up the best path, doesn't find a shorter path. So all we have to do when we launch a whole bunch of these Lambda. So the Lambda is just doing RT star with a few additions. Every time an Lambda, which is just, sorry, let me scroll that a little bit. And Lambda is just a function, just a piece of code that you give the cloud. It takes inputs and returns an output.
But sorry, the contract with the cloud was that it will run it when it wants to?
It will run it when you ask it to.
When you ask it to. So how is that different than the original cloud model?
The prior cloud model?
Yeah.
That wasn't always on like 96 core machine that you turn on.
So this is just a smaller ask
Yeah,
to the cloud.
And it charges you 100 millisecond increments, whereas the spinning up a server is going to stay on until you turn it off, and it's going to charge you, $3 an hour or something.
And so everybody's just running RRT star when the robot's planning, and you're doing your lock-free merges plus this trick in order to combine them? Is there, or okay, cool.
Yeah, and it gets really good speed up.
Other questions? So maybe a controversial question, while we wait for, more people to pitch in. So, in this framework that you're presenting, right, with the last part of this, fog robotics, so another possibility is that, we, instead of doing task and motion planning, right, we learn everything and we deploy it locally on the edge, right? So presumably, a neural network might do the whole task and motion planning, or let's forget task planning, just the motion planning part much more efficiently. So it seems like, there are two directions one can go, right? One is let's make it efficient to work on the edge, and maybe the tool is learning. And one is how do we take all the great things we already have in motion planning, right, and speed it up in the way you are describing. So I'm curious to hear your thoughts.
Good question. I think, my high-level thought is that if you've got an algorithm that you really like to run, but it's really slow, and you need to wait for 10 years for your algorithm to be fast enough to run on a robot, that's a really good argument for using the cloud. So, but it's also, not to say we don't need to make our algorithms better and faster. It's just if we have something that can run quickly now, if we give it enough compute, we can start taking these problems that take more than a minute to compute and make them sub-second and make them really practical for everyday use.
Okay, thank you. So if there are no more questions, let's thank Jeff once again.
Yep.
Thank you, Jeff.